So last time we finished covering finding the length of the arc of a function. So we did a couple of examples. We did derivation. Where is this arc length formula coming from? Today we're going to do another application of integration, which is finding the area of a surface of revolution. And well, remember those solids of revolution? They're coming back. However, they're not coming back to find their volume, but rather to find the area covered by those surfaces. Well, here's the formula. I will sort of derive the formula, like, you know, not in a whole detail, the same way we did it last time for the arc length. Otherwise, it would take basically half a lecture or even a whole lecture. So I will just give you the idea right here. So here's a picture here. So how does that surface area is generated? So essentially, we have this function f of x, which, let me highlight it. And what we're going to do is rotate that length. When we rotate that length, what are we going to generate? Yes, we still generate a solid, if you will. However, it's not to find its volume this time, but rather to find the surface area. In other words, it's like finding the amount of skin, if you will. I mean, but as an area in this case. Well, so the picture here is that, of course, we will find in a similar way that we found like the area under the curve and the arc length. In this case, well, we're going to take this piece of length, which we will rotate, and the final shape that we are going to obtain is something like this. It's like a cone, but it's not quite a cone. It's what we call a frustum of a cone. It's actually a cone in which we chop the cone. Otherwise, if it were the whole cone, you know, it would look like this. It would look like that, right? But we're not looking at the whole cone. Well, so we're going to rely on finding the area of that the surface area of that frustum of the cone, which will be this little partition here. Well, so to find that area, that's A equals to 2 pi RL, okay, where the radius is actually the average radius. It's not, because if you look at this picture, notice how we have, okay, let me move this picture, let me do the picture again. So if we look at this picture, we have a smaller radius and we have a larger radius. So what we want in this case is just to find the average radius. So R will be R, or actually let's call it R1, R2, R1 plus R2 over 2. So that's just the average radii, the average of the radii in this case. And this L right here would be the length of that. It's like the height, but in this case it's really the length of that's the slant length in this case. Well, so to develop a formula for this partition here, if we rotate this again, well, that'll be the surface area. That's going to be 2 pi. Okay, what's the value of the radius in this case? Well, in this case it's the function f of x, and that's because if we look at this, at this distance between the axis of revolution, this is the radius, and in this case notice how the radius is vertical. So because that distance is vertical, that should be equals to y. It's going in the y direction, if you will, but usually we represent y as an f of x. So that's f of x, and L, it's going to be our delta L. Alright? So what is that delta L? Recall that again, we are adding infinitely many of these frustums of cones. So So, and this delta L, recall from last time, this is 2 pi f of x. That's a 1 plus f prime quantity squared. And of course, adding infinitely many of this, what do we get? Isn't it the integral? And have the 2 pi outside. Well, let me call, well, for now it's f of x, but in general it will be r of x. You'll see how it works. Which is really the formula that we have above. All right, let me zoom the whole thing out so you can see the formula and compare. So without getting into too many details, with too many technicisms about the derivation, well, that's essentially how we're going to obtain the surface area in this case. Last time we were adding infinitely many lengths given by the Pythagorean theorem, and you can see that here, you know, it's back in a way. So, but now we're using it to find the surface area. Alright, so there's a couple of things that we need to consider whenever we're finding a surface area. So for example, if we're using functions of x, actually this quantity right here is the radius, is the average radii from the frustum of a cone again. So that's r of x, and well, so that r of x can be the function itself or can simply be x. Well, what is that going to depend on? For example, if we rotate, so let's highlight this. If the rotation is about the x-axis, well, rotation is about the x-axis, it's going to be actually this picture here. So we have that function f of x which is rotated about the x-axis, but notice that distance is going to be, it's a vertical distance, which in this case is given by y, if you will. So this is y, but because we're using functions of x, this y will be exactly that given function of x. Now, when we are rotating this same function f of x, notice this time we have a different setting. So in this case, the rotation is about the y-axis. So what we're going to do in this case is rotate this region, this length, about the y-axis, but notice the distance from the axis of revolution to any point on the function that we are rotating is a horizontal distance. So really this r of x, I mean this radius, it's just going to be x because it's in the horizontal direction. Alright, so this distance right here, that's the distance from the axis of rotation to any point as opposed to this one being vertical. And well, so this is the picture for function of x being rotated about the y-axis and the x-axis. And in this case, well, so the setup for the formulas right here, whenever we're using functions of x, well, so this r of x, which is really the average radii of the frustum of this cone, well, notice in this case how, notice a pattern here. When we're using functions of y rotating about the y-axis, it's always that radius is the function. So let's compare that with the functions of x. So using functions of x about the x-axis, it's f of x. Otherwise it's just x or y depending on the function. Well, so I guess the best way to get this done is, how about we look at some examples. Alright, so let's look at the first example. So we have the curve y equals to x squared, the square root of 4 minus x squared from -1 to 1, and that is an arc of the circle of x squared plus y squared equals to 4. And notice in this case it's not the whole arc, Because number one, question, x squared plus y squared equals 4 is a representation of what geometric figure or what graph? It's a circle. More details about that. What kind of circle? Any other details about that circle?
The radius is 4.
The radius is 4. Close. Well, the radius squared is 4. Recall that this quantity represents r squared, so what would be the radius then? So it's a circle of radius too, but in this case we just want to find the area, the surface area between -1 and 1, so we don't want the whole, in this case it's upper semicircle. How do we know this is the upper semicircle? Because, well, when you solve this circle equation for y, technically you should get to result a negative and a positive radical. In this case, we're just given the positive radical. This means that this is the upper semicircle. All right, so let's have a look. Let's have a look at the graph. So in this case, let's see, Cartesian plane. And -1, -2, 1 and 2. All right, so if we were to get or to find the area under, or rather generated by the entire semicircle, we would have done this. All right, that's the graph of the upper semicircle. However, we don't want the whole upper semicircle. What do we want instead? We just want the upper semicircle that goes from -1 to 1. So basically only this. That's the only thing that we want. All right, what else are they telling us in this case? Well, so they want us to rotate this about the x-axis. All right, so when we do rotation about the x-axis, we are going to generate a solid rotating in that direction. So it's going to look something like this. All right. So just to give you a picture, well, what's the look of this? Well, let me make it look 3D, hopefully. So it's generating this solid. So what's the shape of the solid? Have you guys seen those Parmesan cheese, the big ones, the one that they import from Italy? Not the ones from the back, you know, the big ones. So if you put it vertically, that's basically the solid that we're generating here. It's flat on the sides and it's circular on the edge. So that's the shape that we are obtaining.
Like the area, are we just considering like when you mentioned the cheese, would it just be like the outer layer, or would it be all the area inside?
No, it's just the area outside. Oh yeah, not the one on the sides, just the area. Yeah, you mean this area only, right? Mm-hmm. Yes, that's the only area we're calculating, not the one on the flat sides, right? Mm-hmm. So let's write down a formula in this case for the surface area. So number one, I would start writing the formula in general. So surface area is A, or just big S, that's fine, just big S. That's 2 pi integral from A to B. R of X, that's the radius, so that's the average radius, you know. And that's times the square root of 1 plus F prime of X, quantity squared, dx. Now, in this case, we need to decide what R of X, this looks like a V, let me change it for an R. Okay, what that R of X is that going to be the function f of X, or is that just going to be X? Well, number one, so in this case, notice how we're rotating about the horizontal axis, the x-axis. That means that the distance from the axis of revolution to whatever point on the edge of the graph that we're rotating, notice it's vertical, right? Because it's vertical, that means it's in the y direction. But in this case, since we are to use functions of x, we know y as a function of x. So that means y will be f of x. Okay, so let's set it up. So in this case, that's the integral from a to b. Oh, actually from, okay, let me do for now -1 to 1, and that's the function f of x, that's the square root of 4 minus x squared. And well, from here, oh, we're gonna need the derivative of the given function. So number one, let's spend a couple of steps finding the derivative of the function f of x. So number one, this is y equals to 4 minus x squared to the 1/2. That way, that's so we can find the derivative of the function. Well, in this case, we need the chain rule to differentiate this function. So to find y prime, let me do it over here. Y prime, that's going to be 1/2 times 4 minus x squared to the 1/2 minus 1, that's a -1/2, but times negative 2x, which is the derivative of the inside of the parentheses. So in this case, we can do a couple of simplifications, and we'd better do all the simplifications actually, because we're going to put this madness inside of the surface area formula, which is going to become a bigger madness. So the more we simplify this, the better. You'll see why. So cancel out the 2's here, and this is the same as saying x over 4 minus x squared to 1/2, and that's equal to 4x over the square root of 4 minus x squared. So that's going to be here, and we're going to square it. Right, so let's see what's next. So that's 1 plus that quantity x over the square root of 4 minus x squared, quantity squared with respect x. Whoops. Alright. So yes, this madness looks interesting. So, well, number one, do not attempt to do any U-substitution. Actually, we're going to do some algebra first to simplify these two guys together. All right, so let's see. What am I going to do? Okay, so number one, I'm going to square this quantity inside of the radical. That's going to be 2 pi. The integral from -1 to 1. I'm going to change the limits later, yes.
Shouldn't that be negative for x over root of 4 minus x?
That's what I meant, yes. But ultimately it's going to get squared, so that negative sign is going to get lost. But yes, it's still important to have that negative symbol in here. So, and I also missed it here, right, in the setup. I also missed it here, and I also missed it there. All right, thank you. So that's the square root of 4 minus x squared times the square root of 1 plus x squared over radical squared, that's just 4 minus x squared. Alright. And there's a couple of ways to simplify this really nicely, because number one, so last time we did a similar example in which we had to do the least common denominator, right? So today I would like to take a different approach, and in this case take advantage of the properties of radicals, in particular that one that says the square root of a times the square root of b equals the square root of a product ab. So what I'm going to do here is, that's 2 pi, the integral from -1 to 1 of the square root of the quantity 4 minus x squared times the quantity 1 plus x squared over 4 minus x squared. dx. So what I'm going to do here is distribute everything. I'm going to distribute 4 minus x times 1 and 4 minus x times x squared over 4 minus x squared. So what's going to happen here? So on the one hand, I'm going to get only the square root of 4 minus x squared, and then plus 4 minus x squared times x squared over 4 minus x squared. Whoops, that's actually negative 1 to 1 to pi. So do you see what's going to happen here? See how these are going to simplify? 4 minus x squared, 4 minus x squared are going to get cancelled. Dx. And we're going to be left with 2 pi integral from negative 1 to 1, 4 minus x squared plus x squared with respect x equals, notice how also this x squared get cancelled. That's going to leave us with the 2 pi times the integral from negative 1 to 1 of the square root of 4. But what's the square root of 4? Isn't it just a nice number? That's actually 2 dx, which we can multiply outside with the 2 pi and turn that into 4 pi integral from negative 1 to 1 dx. So another thing I would like to do in this case is to change the limit. But in this case, the way I'm going to change the limit, it's only to take advantage of the symmetric property of the shape that we are rotating. Notice that if we integrate from negative 1 to 1, this is the same as saying 2 times the integral, 2 times 4 pi, the integral from 0 to 1. See what I'm saying? So instead of integrating from negative 1 to 1, we can integrate instead from 0 to 1 and multiply that result by 2. But this trick only works when you know for sure that the shape that you're rotating or that you're integrating over is perfectly symmetric. Otherwise, it's not going to work. So that's going to be 8 pi. The integral of the x is simply x from 0 to 1. So 8 pi 1 minus 0, which is 8 pi units. So that is our first example in finding the surface area, right? Example number 2. Let's repeat exercise number 1. However, this time we will be rotating the region about the y-axis. So again, same function, same limits of integration. We will be using functions of x still. However, things are going to look a little bit differently. You'll see how it works. So hopefully, after looking at this second example, you get the idea on how to treat that r of x in the surface area formula. Y in some cases will be the given function, and y in some cases it's going to be just x or y, well, depending on what kind of functions are we working with. So number 1, let's plot this again. So 1, 2, 2. Again, we don't want the whole semicircle, just the part of the circle that goes from negative 1 to 1. So in this case, notice we are no longer rotating about the x-axis. What we're doing this time, we're rotating about the y-axis, like this. So what is this going to generate for us? Well, it's going to generate this solid right here. right? Well, it's like a cylinder. It's like a cylinder with a kind of a spherical top, if you will. All right. Well, so let's find a formula for, or rather, yes, a formula for this surface area, to calculate the surface area. So S in the first place is the integral from A to B of r of x times the square root of 1 plus the derivative of the given function that we rotated, quantity squared. This means, well, so we need to figure out the radius r of x. Now, number one, in this case, since we are rotating this region about the y-axis, check this out, this distance right here from the axis of revolution to any point on the S of the solid that we generated, do you notice how that distance is horizontal this time? Well, in this case, this r right here, this radius, which is the distance from the axis to the point to a point on the outermost point on the solid, it's just horizontal, it's just x. If we were working with functions of y, which we are not in this case, then we would have said x equals some g of y. And then whatever function of y that we have, we would be using it. However, it's not the case because we are repeating the same settings as in exercise 1 to work, in this case, to still work with functions of x. Well, so this means that's the radius x, simply x. All right, let me see, how did I denote it before? Okay, so that's fine. So just x. So, all right, and I can cancel. Yeah. So this will be I forgot the 2 pi here. 2 pi integral from -1 to 1 r of x, which in this case is x, square root of 1. Well, I'm not gonna have enough space, so 2 pi integral from -1 to 1 x square root of 1 plus the derivative of the given function. But I'm not going to do it again. I'm just going to use the same derivative from the previous example because it's the same. So negative x over the square root of 4 minus x squared, quantity squared, with respect x. Alright? Well, so, oh my god, in this case we will have to do some algebra, a little more algebra than we did before. So this will be 2 pi integral from -1 to 1. Or you know what, how about I write this integral from 0 to 1. We can take advantage of the symmetry from 0 to 1 as long as we multiply by 2 the same way. We can do that at any time in the process. We don't have to wait until we have a simplified integral, so we can do whenever we want. So that's x times the square root of 1 plus x squared over the square root of 4 minus x squared. Oh, actually, no, that's not a radical. So 4 minus x squared with respect x. All right. The reason I left all this space is because this time, okay, let's think of that 1 as a 1 over 1. And how about we multiply by the least common denominator, or rather we find a least common denominator by multiplying by the missing factors, in this case 4 minus x squared over 4 minus x squared. Only then we can combine the fractions together. So that's going to be 4 pi integral from 0 to 1 x square root of 4 minus x squared plus x squared. And well, despite how crazy this looks like, trust me, this is going to reduce really nicely. All right, so this will be 4 minus x squared dx. All right, that's a 4 pi integral from 0 to 1 of the quantity x square root. Notice how these two cancel out, and that's simply going to be 4 over 4 minus x squared. And again, I'm going to use a property of radicals this time. In this case, that property of radicals that tells us that the radical of a quotient a over b is the same as the quotient of two radicals. This way we can simplify, well, like in this case we can see the square root of 4, which is possible to simplify. And so that's going to be 4 pi integral from 0 to 1 x root of 4 over root of 4 minus x squared with respect to x. And the square root of 4, isn't that a 2? Which we can multiply with the 4 pi outside of the integral to give us an 8 pi. And in this case, let's go about writing x. We will be left with the function x over root of 4 minus x squared dx. So let's have a look at this integral. Notice how the problem changed significantly just by changing the direction of the rotation. So for the rotation about the x-axis, in the first example, gave us just a very simple integral, just the integral of the x. In this case, well, due to the algebra that we're required to do, notice we're going to get a different result over here. And in this case, well, let's see. Any ideas on how to evaluate this integral? What method would be the best? U-substitution, right? U-substitution looks good because the derivative of 4 minus x squared is negative 2x to the first power, which we have it over here, so should work. All right. So that means u equals 4 minus x squared du equals to negative 2x dx. That means x dx equals to 1/2 or negative 1/2 du. And well, again, because we have limits of integration, and to avoid all that crazy work of back substituting and simplifying a lot of numbers, and I'm going to change the limits of integration to u of 0 and u of 1. So u of 0, that will be 4 minus 0 squared and 4 minus 1 squared. That's going to be 4, and that's going to be 3. And yes, it's going to look a little weird at a moment, but check this out. So that's going to be number 1, 8 pi integral from 4 to 3 of the quantity 1/2 d negative 1/2 du over the square root of u. So that's going to look a little weird, having a lower limit to be a larger number than the upper limit. So, well, when we integrate something like that, that's going to give us a negative number. However, do you see this negative factor over here? That's going to fix the issue. So don't freak out when you change the limits of integration and you see this weird setting of lower limit to be a larger number than the upper limit. So that's fine. That's very common. But that gets fixed with these negatives. Okay, so let's multiply negative 1/2 times 8 pi. That's going to give us a negative 4 pi integral from 4 to 3. And I'm going to move this root of u to the numerator as u to the negative 1/2 du. Alright guys, so if this is still if this is still freaking you out, having this larger lower limit than the upper limit, you can use one of those properties of integrals that you learned back in calculus 1. Whenever you have the integral from a to b of f of x dx, you can always reverse the limits of integration provided you change the sign of the integral. Alright, and we can do that over here. So alright, let me erase this so I have enough space. Well, actually, I'm going to put it over here instead. So I think it's a good property to keep in mind. So this property, so I'm going to rewrite the integral like as a positive. I'm going to use this negative sign to reverse the limits of integration. So that's 4 pi integral from 3 to 4 u to the negative 1/2, and we may go about the integration at this point. And well, the integral of u to the negative 1/2 add 1 to the exponent, so 1 negative 1/2 plus 1, that's 1/2 divided by 1/2. But careful, dividing by 1/2, what is that equal to? 2. It's the same as multiplying by 2. So 4 pi times the reciprocal of 1/2, which is 2, that's 8 pi. And don't forget the limits of integration from 3 to 4. So this will be the square root of u. In this case, let's go back to radical notation from 3 to 4. And this will be 8 pi root of 4 minus root of 3, which reduces to, well, in this case, the only quantity that we can simplify exactly is the square root of 4, which happens to be 2. So final result, 8 pi times 2 minus root of 3. Okay? So notice how many different ideas were used in this situation, you know, like having to take advantage of the symmetry of this region. What else? So in this case, again, keep practicing on changing the limits of integration to the world of the substitution, in this case the world of u, and other properties like using those properties of integrals to change the order of the limits of integration by changing the sign of the integral. Alright, so let's see. Alright.